Hello students, in this video we'll discuss about decision properties of CFL. So in the previous video we have discussed deterministic contextual languages. How can you say that a language is only DCFL but not NCFL? Sorry, only CFL but not DCFL. Reverse, right? So we'll go with this. What does it mean by decision properties? See, we have already discussed decision properties concept in regular languages. So deciding whether it is true or false, we have to decide, right? Or we have to answer the questions, but without saying that may or may not be. If you say for S decidable, no decidable, somewhere you are saying may or may not be, that means not decidable problem, right? So can we develop algorithm that answer? If we could able to write the algorithm for yes and no, then of course we can say that they are decidable, right? Then is a given string in the language. For example, you have given a machine and every machine accepts language and you have a string. Can you write an algorithm to check whether this string is belongs to this language or not? So you have to say yes or no with your algorithm so that we can say that it is decidable. Of course, if you take the finite data meta, you start reading the string from the starting state, and if the string reaches the final state after completion of all the symbols, we can say that it is member of that language. Yes, decidable. Not only that, all the properties are decidable under the regular languages. But when it comes to CFL, some are not decidable. We'll discuss that. Because is a given string is this is called membership problem. Of course, this is decidable. We'll take with an example how to check it. Is this language is empty? What does it mean? Same. We have a PDA M and every machine is going to accept language. Whether the number of strings in this PDA is empty, right? Whether it is decidable. Or same way, every PDA, right, or a machine definitely represents some language. Is that language number of strings in this language is less than or equal to some value? That is called finiteness. Not only that, infiniteness, completeness, equalness. So we have so many other decidable properties, right? So let me go with that first membership problem. So unlike FS, we can't just run the string through the machine and see where it goes, since PDS are not non-determinists. They are non, like, see, if it reaches the final state, we can say that it is accepted in the finite data meta, but not in the PDS, because a PDA can be accessed in two ways. With by accepting by going to the final state and accepting by making the stack is empty. In both the cases, we can check it. Of course, the problem is decidable anyway. Either it is reaching the final state or stack, we can say it. So, but what you have to do first, we have to convert the PDA. The other way you can do it, convert the PDA to CNF, then start deriving the string from the CNF with 2 power n minus 1 if the size of the string is n, right, in CNF, because CNF means either two non-terminals or a single terminal. For example, if I take it, S tends to AB, A tends to A, B tends to B. So if my string is AA, what is the size of this 2? Then you have to go with maximum of 3 steps. You'll check it whether it is accepted or not. Why? Because say that two non-terminals are a single terminal. Then what will happen? First one is S tends to AB. Then I got A tends to A, B tends to A. See, I got in 3 steps. 1, 2, 3. For example, if your length of the string is 3, something like that. So S tends to AB, B tends to CD, and A tends to A, C tends to C, D tends to D. See, 3 length string we got in 4 productions. 1, 2, 3, 4. Right? Sorry, 5. 5. Because 2 into 3 minus 1. 6 minus 1 is 5. So in CNF, exactly the string will be decided in 2 into n minus 1 steps if the size of the string is n. If can't, then it is not accepted. We can say that, so that's why it is decidable. And emptiness, see, remove all the useless symbols and useless productions from the CNF after converting into the CNF. If your S is useless, even S starting symbol is also useless, then we can say that the language accepted by the grammar is empty. If S is also useless means what? We can't terminate it. Useless means we can't terminate. Like it may be like this. AS. Okay. A tends to SA for something like this. We don't have any termination condition. All are useless, right? Then finiteness, we have to do like the same thing between n and n. So in regular languages, n equivalent to number of states in FA. In CFL, n equivalent to p plus 1, where the p is the number of non-terminals in the context-free grammar. So if there is no recursion among these productions, right, then we can say that the language is finite. Means if you are generating the strings, the number of productions should be in between n and 2n. Run through the membership algorithm. If it passes between these length, okay, then we can say that L is infinite. If fail, L is finite. Let me repeat it, guys. N is number of states in finite data meta. So, but how can you say that finite data meta is finite? Means no self loops and cycles. But as we can't directly apply it on the PDA, how can you check the finiteness in PDA? In finite data meta, if there are no cycles or self loops, we can tell it directly. But in PDA, you have to convert into CNF, right? In the CNF, we are going to have the grammar with the P variables or the non-terminals. Then generate all the strings with the length between n and 2n. Generate all the strings. If the n is nothing but 2p plus 1, means if you are having production 6, you have to take the n value is 13. Then generate all the strings in between 13 and 26 and run the membership algorithm. If it passes the membership algorithm, then we can say that the L is infinite. Otherwise, we can say that it is finite. Means there is a recursion if it fails. Right. So in that way, you can prove whether it is finite or infinite. Right. So let me go with some other decision properties of CFL. See, guys, as I told you, all the properties of regular languages are decidable. Equalness, emptiness, right? But some problems in CFL are not decidable, means we can't write an algorithm to prove it. For example, the best one is ambiguous. We have already discussed. So it is a complete trial and error method, right? It is a complete trial and error method. You cannot prove that the language is ambiguous with an algorithm or the grammar is ambiguous with a algorithm, right? You have to just go with taking the strings and try to construct the more than one parse trees. And another one, this is ambiguous. Another one, equalness, right? Equalness means, for example, we are having two grammars, G1 and G2, and the two grammar generate some language, L of G1, assume that that is L, and L of G2. So the number of strings, then the language generated by these two grammars are same. We don't have any such particular algorithm existed to prove the ambiguity in it. Why? What is the case, right? For example, as we have already discussed that every DPDA is NPDA. We have discussed about it. But every NPDA may or may not be DPDA. May or may not be DPDA. Assume that we have taken one machine which is DPDA and we have taken some machine 2 which is only NPDA but there is no DPDA existed. Then how can I prove that the language exists by the M1 is equivalent to the language existed by the M2? That is not possible because we don't have any conversion algorithm. Whereas if you take the equalness in regular languages are same. For example, if you are having DFA for M1 and NFA for M2, right? Then how can you perform the equalness? Convert this NFA to DFA. We have an algorithm. Then you can run the algorithm on these two DFAs, that will work. But we don't have such a conversion technique here. That's the reason we cannot do it. So not only those two, there are some other problems which are undecidable. See, first one is checking the ambiguity in the grammar. Second one, whether the language is ambiguous. This is the grammar. The next one, language is ambiguous. And another, the closure properties which are not closed, all are undecidable also, like intersection of two languages, complement of a contextual language, difference of a contextual languages, whatever. The properties which are not closed under, they are all undecidable. Which are closed under, decidable, means union is closed. So if L1 is CFL, L2 is CFL, then L1 L2 must be CFL. Must be. Decidable. Must be you are saying, right? But if L1 is CFL, L2 is CFL, L1 intersection L2 not closed. May or may not be. Undecidable. Right? Same way. So whether L1 is a complement of L2 or L1 is, right, subset of L2, these all are, right, whether L1 is equivalent, this one, and this one, either L1 is belongs to sigma star, right, that is completeness, whether it is equivalent to the inverse language. So these all are undecidable problems in the context free languages, right? So in this unit we have discussed mainly about normal forms and closure properties of context free languages, decidable properties of context free languages, right? And what are the languages which are only accepted by the NPDA but not by the DPDA. So that's the end of the third unit. So in the next unit, in the next video, we'll discuss about the 14th concept called Turing machine.